Hi everyone. In the last lecture, we have introduced compact operators and discussed some important properties of compact operators. So let me quickly recall. A bounded operator T between H1 and H2 is said to be compact if T maps bounded sets of H1 into pre-compact sets of H2. So that is equivalent to say that T is compact if and only if Txn has a convergent subsequence for every bounded sequence Xn in H1. And we have shown that K of H, set of all compact operators defined on H, is a two-sided ideal in B of H. It's a vector subspace of B of H as well as it is an ideal in B of H. So today we discuss a few more important properties of uh, the space of all compact operators. So let us look at the theorem. We show that K of H is closed in B of H. Okay. So let us look at the proof. Let K be in the closure of compact operators. Then there exists a sequence Kn in K of H such that Kn converges to K in the operator now. Our aim is to show that K is compact. The claim is that K is compact. So for this we have to start with a bounded sequence in H and show that K of that bounded sequence has a convergent subsequence. Let Xn be a bounded sequence. In H. Now from this bounded sequence we have to construct a convergent subsequence xnk such that K of xnk is convergent. Okay. Now K1 is compact implies K1 there exists a subsequence, there exists xn of 1 subsequence of this sequence xn such that K1 of this subsequence is convergent. Okay. Now xn 1 is a bounded sequence and K2 is compact. So K2 is compact implies K2. So there exists a subsequence. This is a subsequence of xn1 such that K2 of xn2 is convergent. Now K3 is also compact. So there exists xn3, a subsequence of xn2 such that K3 of xn3 is convergent. Okay. In general, we can get so for n. So proceeding in this way, so we can get there exists a subsequence xn. Can say that okay. So xn of k of xn k minus 1 such that we can write j instead of k. such that kj of x and j is convergent. Now we have the bounded sequence x1, x2, x3, x4, so on. So we got a subsequence xn1. So this is, we can write x11, x21, x31, so on, such that k1 of this, let me write xi1, is convergent. Now we get x12, x22, x32, so such that k2 of xi2 is convergent. So proceeding in this way, we can get xi n. So we can get x1 I, x2 I, x3 I, so on, such that kn of xi I, or we can say that ki, this is convergent. Now we want to get a subsequence of original sequence such that kn of that subsequence is convergent except for finitely many terms. So the obvious choice is that we have to look at these diagonal entries. So let us look at, so let us write zi as xi I. Now this zi is a subsequence of the original sequence. In fact, it is subsequence of xni, such that for exceptly finitely many, kn of zi is convergent. So for except finitely many n's, this kn of zi is convergent. So our claim is that k of zi is Gaussian. For all ij n in n, we have consider this k of zi minus k of zj. This can be written as norm of k of zi minus kn of zi plus kn of zi minus kn of zj plus kn of zj minus k of zj. So this can be written as norm of k minus kn, here zi from this one, and this is k minus kn zj, but minus here, minus zj plus remaining terms kn of zi minus zj. If you apply the triangle inequality, you will get this is less than or equal to norm of k minus kn norm zi plus norm zj. Again we are applying triangle inequality for zi minus zj. This is plus norm of kn zi minus zj. Now we know that kn converges to k, and this sequence zi is bounded, so we can make this is less than some fixed quantity. And we also know that kn zi is convergent, so this become Cauchy, the second term. So we can conclude that from this, this implies that kzi is Cauchy in H, hence convergent H, because H is complete. So this completes the proof that K is compact. We have shown that there exists a, we have started with a bounded sequence Xn, and we have extracted a subsequence Zi such that K of Zi is compact. And K of Zi is convergent, hence we can conclude that K is compact. So we have taken K from the closure of K of H, and we have shown that K is in K of H. So from this we can say that K of H is closed in B of H. There is one more important property for these compact operators. The compact operator transforms pointwise convergence into operator non-convergent. So let me write this as a lemma. Let Tn be a sequence of bounded operators such that Tnx converges to Tx for every x in H for some bounded operator T. If K is compact, then we can say that Tnk converges to Tk in the operator norm. Okay. So when Tn converges to T in pointwise, and if you look at Tnk where K is compact, then Tnk converges to Tk in the operator norm. Okay. So let us look at the proof. Suppose this is not true. Suppose Tnk does not converge to Tk in the operator norm. Then there exists a delta and a subsequence Tnj Tnjk of Tnk such that norm of Tnj minus norm of Tnjk minus Tk is bigger than delta. So let us call this inequality as 1. So choose a sequence xn, let us say xni, such that norm of Tnjk minus Tk acting on this xni bigger than delta. So let us call this inequality 2. This follows by the definition of operator norm. Here this ni depends on nj. For notational convenience, we have chosen this xni instead of xnj. So as K is compact, So there exists a subsequence xnj of xni such that k of xnj is convergent. Say converges to some y, because xnj is a bounded sequence, xni is a bounded sequence, so we can get a subsequence xnj of xni such that k of xnj is convergent. So we can say that by 2 we can say that tnj k minus tk xnj bigger than delta. So let me call as this inequality as 3. Okay, now we want to show that tnj converges to, we want to show that tnk converges to tk in the operator now. But we assume that if this is not true, what will happen? So we should get a contradiction. So we have, so by 3, so delta is less than norm tnjk or tnj minus t k xnj. Now this can be written as, this is less than or equal to norm tnj minus t k xnj minus y plus norm of tnj minus t acting on y by triangle inequality. Okay, now let us take C as supreme of norm Tn n in n, because Tn is convergent, so it is bounded. So then we can write, so delta is less than norm Tnj minus t k xnj. So this is less than or equal to, by the above inequality, so this is 2 times C norm k xnj minus y plus norm tnj minus t y. Okay, now k xnj converges to y, so you can make the first term to be less than delta by 8c, and so we can say that this is 2c into delta by 8c. The second term we can make this less than delta by 4, because now Tn converges to t in the operator norm. Sorry, Tnx converges to Tx for every x in H. So from this we can say that Tnj y converges to Ty. So we can make this to be less than delta by 4. So on the whole, this can be made less than delta by 2, which is a contradiction. This is a contradiction. So we got a contradiction because we assume that Tnk does not converge to Tk in the operator. So hence we can conclude that Tnk converges to Tk in the operator. So this result has nice application. You can write as a corollary. Let H be a separable inward space and T to be a compact operator. Then there exists a sequence of Tn of finite rank operators such that Tn converges to T in the operator. So we can conclude that set of all finite rank operators is dense in K of H with respect to sup norm when H is separable. So we can actually conclusion. This set of all finite rank operators is dense with respect to the operator norm in K of H. Okay. So since H is separable, we can choose an orthonormal basis. Let phi 1, phi 2, phi 3, so on be an orthonormal basis for H. So define Pn from H to H by Pn of X as summation j equal to 1 to n inner product X phi j multiplied by phi j. So here X can be written as summation j equal to 1 to infinity inner product X phi j for every X in H, because phi 1, phi 2, phi 3 is an orthonormal, so on, it's an orthonormal basis for H. Every element in the Hilbert space can be written in this way. Now we can easily show that. So range of Pn is contained in span phi 1, phi 2, phi n. So we can say that range of Pn dimension of range of Pn is less than or equal to n, so which is finite. And we can easily show that each Pn is a bounded linear operator on H. Now we want to show that T can be approximated by sequence of finite rank operators. Now we know that Pnx converges to X as n tends to infinity. This is for every X in H. Now applying the earlier lemma, so by lemma, so P and T converges to T in the operator now. Okay, now range of P and T is contained in range of Pn, that is a finite dimensional. So therefore P and T is a finite rank operator. So we have concluded that given any compact operator T, we can approximate it by sequence of finite rank operators in the operator. Okay, so from this we can say that the set of all finite rank operators is dense in K of H with respect to the operator now. Now using these results, we can actually get many more examples of compact operators apart from finite rank operators. So let us see few examples. So define D from L2 into L2 by D of x1, x2, x3, so on as x1, x2 by 2, x3 by 3, so on for every xn in L2. So we want to show that this is compact operator by using the earlier approximation theorem. So define dn of x1, x2, x3, so on as x1, x2 by 2, so on xn by n, and remaining terms 0. Now dn is a finite rank bounded operator. So note that dn is a finite rank operator on L2, and we can easily show that dn converts to d in the operator now. Hence we can conclude that by the earlier result d is compact operator on L2. So in fact this can be generalized furthermore. Okay. So let us take a bounded sequence in L infinity. Bounded sequence, define t from L2 into L2 by t of x1, x2, x3 is mapped to lambda 1 x1, lambda 2 x2, so on. This is a diagonal operator with diagonal entries lambda 1, lambda 2, lambda 3, so on. With respect to the matrix of T is diagonal matrix with respect to diagonal matrix with entries lambda 1, lambda 2, lambda 3, so on. So if lambda n converges to 0 as n tends to infinity, then using the earlier method, approximation method, we can conclude that T is compact. In fact, the other way is also true. If T is compact, then we can show that lambda n goes to 0 as n going to infinity. So that result will be proving at a later stage. Okay, so this is one example of operator which is compact but not finite rank. Let us look at few more examples. So let D be as above and R be the right shift operator. On L2, then we can say that RD and DR are compact because set of all compact operator forms an ideal, and we know that D is compact and R is bounded, so RD and DR both are compact. So let us look at one more example. Let us take a two variable function in L2 AB cross AB. Define the integral operator kf at S as integral a to b kst ft dt for every f in L2 AB. We have shown that this is a bounded operator. We have shown in the beginning that k is bounded operator on L2 AB. Now we want to show that it is compact. So let us start with an orthogonal basis. Let phi m n in n be an orthogonal basis for L2 AB. Then we can show that if you define psi mn of st, this is phi m s into phi mt for all st in AB. This is an orthogonal basis for L2 AB cross AB. Okay. Now k, that variable or two variable function k is in L2 AB cross AB, so it can be represented using this orthogonal basis. So we have k of st is summation mn going to infinity k psi mn multiplied by psi mn. Okay, this is the representation for k. So we can do. Okay. Now define Kn, a two variable function from Mn equal to 1 to capital M K psi Mn multiplied by psi Mn. Okay. And define the integral operator Kn f at s as integral a to b with respect to this kernel Kn st ft dt for every fn l to ab. Now this k suffix n, that kernel is a finite rank kernel. So from this we can say that Kn is a finite rank bounded operator. Now we know that as Kn converges to k as n going to infinity, so we can easily check that this integral operator Kn converges to k in the operator. Now k suffix n is a compact operator, hence we can say that, so therefore k is compact. Okay, so this is one of the important operators which led to the development of theory of compact operators, and this is also connected with Green's functions in PDE. Okay, so in the next class we will be discussing about representing compact operators, and later we will extend those results to the general case. So I'll stop here. Thank you very much.